Hello, everyone, and welcome to another edition of the IMTS Conference. I'm Elizabeth Modick, editor of GIE Media's Manufacturing Groups of Magazines, Today's Medical Developments, Aerospace Manufacturing and Design, Today's Motor Vehicles, and Today's E-Mobility. If you have questions for Jason, please type them into the Q&A section, and we will attempt to answer as many as possible at the end of his presentation. First, a little bit of background on Jason. He is the president of a newly formed KYOCERA SGS Tech Hub in Danville, Virginia, and is responsible for leading the development of this advanced technology, research, and specialized manufacturing subsidiary for global conglomerate KYOCERA. Jason Wells has nearly 30 years of experience in all facets of the high-end cutting tool market and has traveled throughout the world working for tool manufacturers in China, Korea, Japan, Germany, the UK, and the United States, which has given him a unique perspective of manufacturing. In today's presentation, Jason's focus will be on the benefits and challenges of incorporating combination tool design strategies to maximize efficiency within an application and capitalize upon productivity gains. Through the course of the presentation, real case study data will be used to outline specific questions, specific outcomes that have been provided, competitive advantages to end users in their processes by embracing out-of-the-box tooling concepts and strategies. Jason, welcome, and the floor is all yours.
Thank you, Elizabeth. I'm going to share my screen now. Good afternoon. It's an honor to be here with you this afternoon and to be able to present this information for you. I wish it was in person, as I miss a lot of my colleagues and friends in the industry since IMTS was canceled this year, but I do appreciate the opportunity to share this information to you in this unique format. As mentioned, I am the president of a newly formed division of KYOCERA SGS, part of the cutting tool group of KYOCERA here in North America. What my division focuses on is special tools and engineered solutions. And the topic I'm going to talk about today is multi-operational tools or combination tools, where we try to really engineer a solution by combining multiple operations into one tool platform or one tool. And I hope today to really enlighten you and help share some information on advantages this kind of strategy can bring to your operations. I'm going to break this topic down into 4 distinct areas. The first thing I want to look at is it always comes down to dollars and cents. So we'll talk and discuss about the cost of machining so we can understand how combined tooling is going to influence that. We'll then look at machining a feature. What do we do? How do we approach it when we get an opportunity? And how do we decide if combination tooling is going to be ideal for us to pursue? Then we'll look at how, by combining some of those geometries into one tool platform or combining some efforts, we can maximize our yield and maximize our results. And finally, we'll talk about things to consider in deciding if we want to go the path of combined tooling. Obviously, this is going to really lean towards advantages in combined tooling, but I do want to emphasize at the end that it's not a cure-all for everything. So let's first look at the cost of machining, and we'll break this down into really 3 areas. It's certainly all about the profits, but we'll look at how combined toolings can really help us seek out profits. What are those areas that it really addresses that helps us maximize our profits and maximize our yields? We'll then look at the cost of machining, the equation of the cost of machining and how that breaks down, and then how the tool itself can impact that cost equation. So when we look at it from a profitability standpoint, the manufacturer of machine parts, it's all about the revenues and the profits, and that revenue and profit comes in that end product that we're manufacturing. That profits are made in the process itself, and anything outside of the manufacturing of that end component that we're going to sell to our customer is just a cost. there's really no profits to be found in any kind of non-productive activities. And this is really what we focus on a lot of our effort when we try to design solutions or engineer solutions is where can we really eliminate or minimize non-productive activity? And what I mean by that is tool change time or detecting broken tools or probing cycles or just general traverse motion inside the machine. We want to minimize that activity so that we can maximize our yield in regards to profits and productivity. And what we find in a lot of applications is the greater the number of tools that we utilize, you can imagine that this just compounds the burdens and the cost and the time in that machining environment, thus compounding the cost of creating that component that's going to be then sold back to our customers. In a lot of machining environments, the actual act of making chips or manufacturing that, machining that part can account for as little as 5 to 20% of the actual cycle time. So for us as tool manufacturers, that gives us anywhere from 80 to 95% of an area we can really focus a lot of attention on trying to reduce and have impact for our customers when it comes to developing solutions. The purpose of this presentation is really to share with you how the incorporation of combined tooling as a strategy can really impact your profitability, your throughput, and your efficiency gains. What we find is, unfortunately, a lot of customers potential customers and end users want to shy away from combination tooling in their operations, a lot of times due to economic concerns. Combined tooling does fall into a category of special or custom tooling. As I said in the very beginning, that's what my division focuses on, which is why I'm talking to you about this today, is that special tools or those custom tools or non-catalog product. And the truth of the matter is they do often have a higher upfront investment or a higher upfront cost for a lot of those special tools. Unfortunately, this feeds into a perception that higher tooling costs means higher manufacturing costs. Unfortunately, because tools are perishable in the equation and constantly being purchased and bought, there's this linear relationship in our mind that if I buy more tools, my manufacturing cost is obviously higher. And the reality of it is it's not that cut and dry, it's not that black and white or that linear. In fact, in a fully optimized application, this couldn't be further from the truth. So we get this incorrect emphasis placed on the direct cost of that tool impacting that direct cost of the tool equaling the cost of our machining process, as opposed to really focusing in on the impact that tool can have on the total cost equation of machining a part. There's been multiple studies. I'm sure many of you may have seen them throughout the course of your career and your travels and various trade periodicals, but definitely several industry studies that have revealed and shown the actual cost of machining a component. And they all kind of boil down to about the same equation. We've seen them in trade periodicals. We've seen organizations like AMT and large companies like Boeing all do these analysis and basically come down to the same end result. And this kind of breaks down what we see typically in the machining environment, machining equation. And as you can see, that tooling section of the cost equation or this cost pie is the smallest component or the smallest piece of the overall cost of machining a part. And again, I'm sure many of you are familiar with this, but I just want to emphasize this as it pertains very much so to this particular conversation. So let's look at the tooling impact. So every function that goes on inside of a facility is really geared around trying to get that end product, that product that we're selling to a customer out the back door so that we can get compensated for that work. But every function is dynamic and it's connected, and every function has a cost associated with it as well. So anywhere where we can produce a savings in that chain of events of creating a product from a quote to a finished product that we're receiving a check for, has those savings have a ripple effect back through the whole series of costs that are associated with our manufacturing and our operations. So let's take a look at the tool, for example. Our tool can have a massive impact on things like our labor costs. How many times does a tool crib attendant have to possibly touch it or set it? The machinist, how much does he have to finagle with it? The programmer, quality assurance people, those are all touch points that the performance of that tool can have an impact on those costs. Machining costs are very obvious, tool change time, those unproductive times that we talked about, positioning moves, fixturing costs, our burdens, our overheads, how many tools do we have to inventory, shipping and receiving folks, purchasing activities, capacity, energy consumption, and then finally material, things like scrap, material removal rates. All those costs are going to be impacted by the optimization and the performance of our tooling and our machine application. As we dissect apart this pie chart, we can really put it back together, and it really can reveal for us the critical role that this smallest slice of cost, this littlest piece of the cost equation, can really impact our overall cost savings. So let's take a look at a machining feature, and let's talk about it a little bit. So we get this opportunity to create a component. We look at it feature by feature. We approach that application, and then we define a process around it, and then we talk about our times. So let's look at a very typical application. And when we look at something that feels so obvious, and it's not illogical to do this, our mind just wants to start to walk through it piece by piece. So what we have in this situation is we have a workpiece component that has a hole in it that has a top chamfer and a bottom chamfer. And thinking in a very conventional, straightforward fashion, we start thinking about, well, I've got to obtain a tool to create the hole. The hole has a surface finish on it, so I got to make sure I create that finish. I got to create the top chamfer and the back chamfer. And as we dissect that and walk through it in our minds, it's very common and very easy to just follow the obvious path of, I need a tool to do this, I need a tool to do that, I need a tool to do this, and just kind of step through it step by step, process by process, addressing each individual geometry of that feature as opposed to the feature as a whole. It's not uncommon for us to not be able to see the forest through the trees. So again, I want to emphasize that this is a very typical situation and a real world situation that we run into. So we could see, just to create this one feature, where we would drill it, potentially ream it, bore it to get the finish that we need and the size that we need, a tool for the top chamfer, a tool for the back chamfer. A very common way to process this particular application. So as we kind of dissect it that way and we start laying it out and putting it feature by feature, now all of a sudden we have to address each one of those pieces of each attribute or each piece of geometry within that feature. So we create our process sheet, we figure all that out, and now all of a sudden we start laying it out and realize we've got 4 tools. We have 4 tools that we have to source. We have 4 tools that we have to make sure that tolerances are cohesive with each other and going to work well together. We have 4 tools to purchase, 4 tools of inventory, 4 tool holders to hold these tools, 4 tools to set, 4 tools to program, 4 tools to monitor tool life, performance, get the right balance of speeds and feeds. We take up 4 positions in our automatic tool changer. We have 4 changes, position moves within the machine environment itself. And then finally, it's 4 tools for our operators, our machinists to set and to handle inside that machine environment itself. So as we kind of break it down and lay it out and visually look at it in that perspective, it quickly becomes apparent how all these non-cutting or non-revenue generating activities get amplified or multiplied as we add tools to the application, add tools to the scenario to machine this particular feature on this part. So beyond the obvious cost to support 4 tools, all the resources that are going to be needed to support those 4 tools, we also have to look at it from a time standpoint. So each one of these tools have got to be able to move into position to remove their small piece of material or their small feature within that, or their small piece of geometry within that one feature. So as you look at it here in this simulation, as you can see on this particular slide, as we add tools to the steps or add tools and steps to the process, it's only natural that that translates out into time. It's not just the time of actually cutting and removing material, it's all that other motion that we really want to try to eliminate and try to get out of the way. Again, that 80 to 95% that we really want to focus in on. So just talking about getting the tools to the workpiece before we even actually remove material, we can see a lot of time. So, and how it multiplies as we add more tools into the application. For example, let's say just to swap out the tools, it's a shift change and your operator, your machinist has to take the used tools out and put new tools into your ATC, your automatic tool changer. You know, let's just say it takes 1 minute to do that, times 4, now you've got 4 minutes. Then you got to take those used tools out, put new tools into holders, set them, measure them in the presetter, set all, everything the way that it's supposed to be set so it's ready to go back into the machine. Say 5 minutes of tool there, multiply by 4, now we're looking at 20 minutes. And then inside the machine itself to move into position and then to swap out inside the automatic tool changer, let's say 13 seconds of tool there. So when we add all that up and it starts to compound itself, we've got nearly 25 minutes of touching that tool, managing that tool, messing with that tool, just to get each one of them, you know, up to the workpiece to do what they're supposed to do from a metal cutting perspective. So let's look at how we might be able to gain some efficiency. Let's talk about how we might be able to grow a better strategy by using a Swiss Army knife approach of one tool with multiple purposes, how that may optimize to help us maximize our yields, and how that's going to impact our productivity and our time. So one of the here or to potentially work with our with end customers is we try to start sometimes looking at the whole or the feature from a different angle or a different perspective. And what I mean by this is sometimes we start with what's the end goal and work our way backwards. I like to use the analogy of proofreading a paper. You can write something and read it a million times the same way and your brain skips over mistakes. All of a sudden, if you change the way you read that, even the setting in which you're reading it, or if you read it backwards, or if you skip around on pages, all of a sudden errors start to jump out at you. It's the same with the application. Sometimes we have to look at it totally different and force ourselves to try to find a better path of profitability. One of the really ways that we start off on whether we want to consider combination tools is when we're given an application where it's one feature. Like I said before, that was just one hole. Yes, it had chamfers, but those chamfers were a part of that one feature. So if we have one feature that's being addressed by multiple tools, that's usually a really good starting point for us of, it's one feature, can we do it with one tool? Kind of an approach that we start to try to wrap our mind around and start going down that path. It's not as if that we were drilling the hole over here and creating chamfers on a whole nother part position and on that part. It was all congruent or all geometry that flowed together. So there is a way that we should be able to approach that with a one tool strategy. And then as we start to look at it, if we can do this with one tool, how's that going to impact our non-value added activities, those activities that really drag on the operational costs of our business? So again, you can see on this screen that original kind of quick gut, here's how we're going to do this type of approach, the very traditional, conventional approach, but that's not the way we want to go. And you can see how much was involved with that. Now let's look at doing that one feature with one tool. It's going to create those 4 aspects of geometry. We're going to create the hole, we're going to finish it the size and surface finish requirements, we're going to create that top chamfer and that bottom chamfer, but do it all together, all as one. So what that does now is it gives us the opportunity to have one tool to tolerance, one tool to worry about the tolerances and how they all fit together, one tool to purchase an inventory, one holder, one tool to preset, one tool to program, one tool to monitor for loads, for forces and all of those things, one position in our automatic tool changer, which is great for any kind of lights out operations. One tool that has to position itself and move within the machining environment. And finally, one tool for our machinists and operators to have to manage right there at the machining environment. So just saying it out loud, just seeing it on paper, you can see the amount of variables that we've removed that could potentially go wrong in a series of events by trying to condense it down into a combination tool strategy. So now that we realize all these other costs and the impact and how we can really streamline touches as something moves through our facility, and the different points that, and the potential to have cost savings ripple back through by minimizing those touches in that motion. Let's really look at it from a capacity perspective, because it's not just the standpoint of what's happening offline outside the machine, but also what's really happening in the machine. So we have one tool that's able to create all those features, all that geometry together in one motion inside that machine. Now all of a sudden we gain capacity, we gain time, we minimize, we start to have a massive impact on that non-cutting, non-productive motion going on inside of our machining environment. These gains are incredibly valuable, more valuable to us in many ways than just not having to buy 4 tool holders or set 4 tools offline or anything like that, because now we've gained the ability to take on more work. We've gained the ability to quote more aggressively on some lead times and things of that nature. So it becomes a lot more about working smarter, not so much as working harder. We get into a lot of situations, and I'll show you some later on, to where customers call us in and really all they want to do is speed up what they've already had, and we're able to re-engineer and reapproach so that we can try to approach things a little bit smarter to try to maximize those savings. So as I mentioned before, this is not a made-up scenario. This is a real-world situation, and it's not an uncommon one either. You saw the simulations in the previous slides. Now I want to show you actual video of a tool similar to this concept that we've talked about in action. So when we display it visually, you can see the layers of costs that are involved in supporting multiple tools. We saw the layers and all the touches with all the holders and the inventory and the purchase orders to get all 4 of those tools together, and all the space and touches. But beyond these obvious layers that we've discussed, it really, the real impact comes down into capacity and efficiency. Gaining that capacity to take on more work, gaining efficiencies to grow your profitability. If we look at it purely from just the, not talking about all the other outside peripherals and just the metal cutting activity itself, we realize tremendous cost savings, and again, attacking that 80 to 95% of non-cutting activity that's estimated to happen inside that machining environment with unnecessary movement and tool changes and things of that nature. So as you can see from this video, the feasibility of this, but also by combining those operations, not just the feasibility of that one feature, but being able to do potentially multiple features. One aspect that also is nice with combination tooling that I'd like to mention is quality aspects or quality opportunities to help drastically improve certain situations where we may have complex features with tight dimensional tolerances. There's an opportunity there for us as tool makers to do all the heavy lifting for you and put it into the tool geometry itself. Also, with a multi-step or multi-tool operation, we have to worry about, sizing tools that follow other tools. We have to make sure are we leaving enough material? Are we leaving too much material? Have we changed the condition of the material for the tool that's going to follow? These are all variables that we're layering into the application. These are all variables that are points that could potentially go drastically wrong for us, unfortunately. So, as I mentioned earlier, the tooling is the perishable part of this equation. It is why it gets the most, gets a lot of attention. It's a focal point when it comes to machining costs. Hopefully what you're seeing now through some of the slides that have built us up to this point is that it's definitely more complex than that. It's definitely more layered than that. I think only equating my cost of machine to the tool is very one-dimensional, and it's much more dynamic, much more complex than that. To try to help further this point, I wanted to put it really into numbers, into dollars and cents, because at the end of the day, that's what we're striving for is that profitability, that ability for us to grow our businesses and supply our customers. So what you see on this particular slide is a cost analysis sheet, or a portion of a cost analysis sheet that we use when we work with customers. Really what I want to focus in on is the green column and the white column. The white column is a total of the 4 tools together, which you'll see outlined in the purplish blue columns. And I just kind of want to lay it out and show you side by side, again, from a monetary perspective. So at the very top of this, we see a cut time. This is the actual cut time in the machine. So on the 4-tool strategy, we had a minute 49-second cut time, and on the combined tool, we had a 47-second cut time. We're trying to do 5,000 holes at a shop rate of $65 an hour. You can see the tool change time in D, E, and F. And again, on the 4 tools, we have to combine that for tool change time for each one of those individual tools. And then at the very, in G, you'll see the number of parts produced with a new tool. And then you'll see the tool cost in row C. So one of the things I want to point out here is, again, that instant thought process of the special tool, the combination tool, having a higher upfront cost. Yes, very true. And as you can see here, we had almost $188 costs on that particular tool. The 4-tool strategy, even combined, was less. It had $128 cost. What we end up with a lot is, it's very easy to go, oh, look at just the drill cost and say $35 for a drill compared to $190 for this combo tool, and then get turned off relatively quick, unfortunately. But again, even with the higher tool costs on the combined tool, as we go down into that sheet and we look at the total machining costs and we bring it across, and again, this is going to be based off of that cut time, driven heavily by that cut time, we can see a massive savings there. We can also see a savings at the tool change cost, because again, we're dealing with 1 tool change as opposed to 4 tools. And then the bottom line is the cost per part on the 4-tool strategy was at $2, whereas on the combination tool, we were able to drive that cost down by eliminating a lot of that non-productive movement and time in the machine down to 89 cents per part. So I want to further demonstrate this just to kind of really clarify the impact that saving time has for your operations as opposed to just looking at that tooling cost. So in this situation, everything remains equal, except in this particular example, I took the tool price and I tripled it. So let's say the combination tool is 3 times as expensive as buying those 4 tools. Still, as we work down each column and get to the bottom, we find that yes, the tooling cost goes up to 93 cents per, or the cost part goes up to 93 cents per part, but still it's less than that $2 per part on the 4-tool strategy. One other example here, we'll say we'll take that tool cost and we'll put it back to its proper place. So $128 combined versus $188 on the 1-tool strategy. But we'll take the tool life down to 1/3 of the 4-tool strategy. So let's say the combination tool can only do 1/3 of the number of parts or the number of holes as that 4-tool strategy. Again, working down the numbers, because we saved so much time in that machining environment, so much non-productive time, we had such an impact on cost. Again, our cost per part comes up slightly more to 97 cents a part, but again, still less than the $2 per part that we see with the 4-tool strategy. Now, taking the very worst case scenario, again, just to further solidify this point, let's say that the combination tool costs 3 times as much. We got a third the tool life. Still, the cost does creep up per part to $1.08 per part, but still less than the 4 tool strategy at $2 per part. Because again, time is more money. It's our precious commodity, but it's also where all of our money is tied up. And then going to a totally ridiculous standpoint, just to make a very important point here. Let's say that you were able to buy those 4 tools for $1, and the combination tool cost you $1,000. And let's say the combination tool can only do half as many holes as the 4 tool strategy. Still, the cost comes up to $1.25, but still less than the 4 tool strategy at $1.98. One of the things I want to point out, though, and one of the reasons I added this, as ridiculous a scenario as it sounds, is I wanted to show the impact that just saving or going cheap on tools really has to your bottom line. So again, we took $127 off of that 4 tool cost. We took it from $128 down to $1, and it only attributed to a 2 cent per part cost savings on the bottom line. So again, the math itself reveals what a small piece of the cost equation to machining really contributes. So that's why it's really important that we try to not get too tied up in the cost of the perishable equating to our cost savings. So in our application with our customer, when we came in at 5,000 hole usage, the cost to use the 4 tools, the 4 different tool strategy was just north of $10,000. When we were able to plug in the combination tool and address that whole feature and with 1 tool in a very consistent motion, we're able to drive that cost down to less than $4,500, or basically create a 56% cost savings, or create 56% less cost. So let's talk about some things to consider when we want to move towards combination tooling. In doing so, the first thing I want to do is share with you some further application examples. We went through a very simple example, but a very powerful one. I hope you found that seems very obvious and maybe not so straightforward that, hey, this is a great opportunity to use a combination tool. But I want to show you some other applications that our company has gotten involved in to really combine operations into 1 tool in order to bring some real savings and have some real impact for customers. This first example is a grooving tool. This was a customer that was actually performing or creating a product on a lathe where they were drilling, and then they were turning a series of internal O-ring grooves into a component. They called us in actually to help with the drilling cycle, but when we got in there, we found that there might be other opportunities. So as we looked at ways we could engineer this product, what we thought about was a whole different way of looking at it from a milling perspective. So rather than just doing all this work on a lathe, being able to put it in a mill, put all those O-ring grooves, all that form into a milling cutter, and then interpolate the internal features on that particular part in one motion. This was a massive savings for this customer who had to add a half shift in order to try to keep up with demand, so that we were able to eliminate that half shift and really able to open up some capacity and remove a major bottleneck. In this particular example, this is a very good situation in the sense that this customer came to us just basically asking us to just quote what they already had in hopes that we were going to quote it cheaper and deliver faster. And the truth of the matter is, again, we could maybe price those tools cheaper, but we'd only have minimal impact for that customer, only addressing really that 3% portion of that cost equation if all we did was just replace brand A with brand B. So we asked if we could get involved with the project, learn a little bit more about it. What we found was that this customer was creating a series of timing teeth And they were using a tool to rough these slots, and then they were coming back with another tool to finish them out and size them, and then they were using a third tool to radius the top of these teeth. So we looked at the application, we used a little bit of a different programming strategy, and we were able to rough, finish, and create that top radius all in one motion. And we were able to take their cycle time from 30 minutes per part down to 1 minute and 30 seconds per part. We had addressed 95% reduction in their cycle time. So we did a great job of addressing that 80 to 95% I was talking about earlier in that first slide. And obviously reduce their tooling, the amount of tooling that they had to handle and inventory and put into tool holders by 66%. This was an application where a customer was creating these seats, almost like counterbores with an end mill, and then coming back in with a drill and created a hole in the bottom. We got involved in the application because they needed to gain time. They were at risk of losing the job because of cost and delivery issues and constraints. They were having issues, also some quality issues with the hole positioning at the bottom and some burr issues. And in this application, our field engineer was able to get involved, look at the application, and realize we could possibly do this. This was one feature with, different pieces of geometry in that one feature, but again, going from that whole mindset of one feature, one tool, and we were able to create the whole geometry consistently, drastically improving the positioning quality issues and concerns, and address that whole application in one motion. This was an aerospace application where customer was trying to create a hole that had some features on top, on the bottom, and it also had a form that blended into the top and bottom features. We did try our best to get this into a one-tool platform, reduce it to one tool, but this is where you really have to use the right strategy and make sure that you're not trying to do too much with one tool. We ended up having to back off a little bit, but we were able to take it from 4 tools down to 2 tools. The one thing that you have to be cautious of is sometimes trying to do too much with one geometry can have a quality issue in certain aspects of that feature, and that's why a proper strategy has to be planned out. This is a great unique tool that we're really proud of that our colleagues over in the UK have developed. We have a tech center, tech hub, very similar to ourselves that services Europe out of the UK. It's called KYOCERA SGS Precision Tools Europe. They do a lot of special tools, combination tools. They have a highly skilled staff over there that gets involved in a lot of solution sales. And in the process of doing that, they developed this particular tool. We are pursuing patent rights on this particular concept in this tool, but basically this tool will drill, then interpolate mill to size, then it'll precision bore the hole, and then finally create a countersink on the top surface. It allows you to create a lot of different sized holes, gives you some process control on precision holes. And our hopes are that this tool really allows us to start to gravitate some combination strategies closer to standard product type of mindset mentality. But really our UK staff did a phenomenal job on a really clever design we're proud of. And then this is an application where we had a customer that was machining parts. The part after the machining application had to have an edge break or a burr removal. It was being done offline in a secondary operation. The first customer tried to do it in the machine itself with 2 different tools. It was adding a lot of additional probing cycles, and a lot of additional time. They were having some programming match issues, so they abandoned that strategy, went back to secondary ops to manage this type of scenario. And our field engineer, again, this was again another UK application, but our field engineer was able to see this and see an opportunity to work with our manufacturing folks to develop a product that was able to mill and break that top edge at the same time. So those are just some examples to just kind of, really pushing, thinking outside the box, looking at things a little bit differently. But does combination tools make sense? And this is where it gets a little bit where we really have to ask ourselves and really dig into challenges within the application environment. Um, like in machining, where we're playing this game of compromise, where we're trying to address whatever the weakest link or the weakest portion of that application is, and we got to have to work around that. It's the same with our strategy on combination tools. That combination tool is only going to function as well as the weakest aspect of geometry within that tool. So, you know, that whatever the most vulnerable piece of geometry on that tool is, that's going to ultimately dictate the tool life of that combination tool. So we got to make sure that we're getting the proper balance of performance, tool life for our customer, and not trying to do too much with one tool. A lot of times, and as you've seen in the pictures and hopefully the various slides that I've shown so far, we have to sometimes extend the length of the tool out in order to get pieces of geometry or aspects of functionality along that tool. And when we do that, sometimes we can run into reach issues when trying to use combination tooling, where we might be restricted by fixturing. You saw some of the tools where we had to reach down below the part, and sometimes we don't have enough travel to get below the part or beneath the part. Another situation that we have to consider too is, you saw on some of those combination tools, we have to create some necks or some thin cross sections in order to accommodate for pass-throughs or going around certain features. And sometimes this can affect the rigidity of that tool. And so sometimes we got to be cautious if we're not getting too thin or too long, that we're not going to run into a deflection issue or deflection situation that might translate out into surface finish issues or any kind of tolerancing or other issues such as that. So as dynamic as the environment is, you know, we got to make sure that we're accommodating those various challenges, those various variables in the most intelligent way possible to take full benefit of that balance that we're trying to seek, and not trying to put too much into one particular tool. The other thing too is it always boils down to economics. It always comes into play with economics. We do find that combination tooling does lend itself better to volume-driven manufacturing, or manufacturing where there's a standardized regular flow of components that are always coming through a facility. It becomes a little bit more challenging in a prototype shop or an R&D type shop, but if we have standard components that have features that we can address with combination tooling, we can really reap the full benefits of really large cost savings in those environments. The other thing too is try to keep combination tooling in mind as an option. Where I have seen it work in R&D or prototype shops, or where they may have a part that has features that are fairly complex and blend together with tight tolerances, where you may have an angle running into a radius, running into a diameter change, into another radius, or so on. When all those geometries need to flow together, come together in a very tight and controlled fashion, that's where combination tooling can solve a lot of issues and can solve a lot of problems for potential customers, because that puts all the burden on us as tool makers. It puts all the weight on our shoulders to make sure that we're tolerancing and grinding those tools and manufacturing those tools within the needs that translate out onto the workpiece surface. And although I did mention, you know, really think about things as one feature, one tool, that's a great launching pad, but don't limit yourself too much. Don't get too much into a box. And hopefully that's the one theme that's kind of underlying here is, you know, thinking outside the box. But, you know, if you have a tool that has some features on it that can be useful elsewhere, then don't be shy about applying those in your machining environment. For example, if you have a tool that's going in and drilling, milling, and chamfering, or creating a countersink or a chamfer on a surface, then use that chamfer geometry to maybe do some edge breaks elsewhere on that part, or do some other things on that part. Really try to utilize and get the most out of your tools, out of your looking at your workpiece as a whole. Here's my shameless plug. I would strongly suggest working with your tooling vendors to really analyze and identify what options are going to work best for you. I say it's a shameless plug, but as someone who's very, very proud to have spent his entire career in the tooling industry, I think one of the things that we as tooling people have a tremendous opportunity of is being exposed to so many different industries, so many different applications, so many different materials that we get involved with. And hopefully we're able to bring that to our end customers and cross-pollinate from lessons learned in other industries that may not naturally cross-pollinate into industries. It, and maybe expose some ideas because of some of the things that we've been exposed to. So again, try to keep in mind one feature, even though it may have multiple dimensions, is it feasible to do it with one tool? Ultimately, what we're trying to do is take that tool and have the greatest amount of impact in your application environment on time, on cost, and on quality. And if we do our job right, then that's going to translate out into the operational efficiencies and profitability that your organization is hopefully seeking. So with that being said, that is my presentation on combined tooling. And I thank you for your attention, and I'm open to any questions that you may have.
Great. Thank you, Jason. That was very interesting. And we do have some time for questions. Let's start with, could you explain how variables in the machining environment, such as the machine itself or tool holding, may influence my choice in using combination tooling in an application?
Sure, yeah, definitely. Sometimes we get into environments where the machine may not be rigid enough, or we get into situations where some of the programming can be complex enough, or processing power needed, that we may have to step back and not necessarily be able to embrace combination tooling. In regards to tool holding itself, sometimes we run into situations because of the way you're putting so much geometry on one tool, you sometimes do have to worry about tool balance when you go to put it into the tool holder, and making sure that you're not creating any kind of unbalanced situation, or a situation that might add, again, additional variables that we have to contend with. So again, that comes with making sure that you have a strategy that's taking all of those variables into account when you design the tool.
Great, thank you. And here's a question on, are combination tools as easily serviced or reconditioned as standard catalog items?
That's a great question. And typically, the honest answer is no. Typically, combination tools are often a one-shot tool, and then you got to purchase another new tool. So that is definitely a disadvantage in combination tooling. Whereas if you have a drill and a countersink and a reamer, you can get those individually reground or serviced and maybe get multiple uses out of them. Depending on how much geometry is on that combination tool, they can be serviced and we can address them. But it's not always feasible. What we do find sometimes happening is one aspect, as I was talking about earlier, one aspect of that geometry could wear out faster than the other, and we may only have to worry about reconditioning it. So if we had a situation where we had a drill and an end mill combined, and the end mill was wearing out faster, we may just be able to go in and recondition the end mill edges and get a little bit more service out of that particular product. But typically they are a one-use type tool.
Great. Well, there are some options there, though, as you said, could be
There
just
are.
one.
There are.
And continuing on, they have a follow-up. Is it true that combination tooling may not be as forgiving in an application as conventional tooling?
It is. That is true. That can definitely be true. Again, as I was explaining earlier, we do have to tweak the geometry, make some compromises in geometry to try to get all of those features on one tool. And at times that can limit how hard you can push the tool or how aggressive you can go after the workpiece. Whereas you may have, for example, like where you're drilling holes, if you're using just a drill, you may be able to go after creating that hole much more aggressively than you could with a tool that may have a neck on it in order to reach through that hole and do a top chamfer or do some sort of milling feature.
Great. And earlier you had discussed a challenge with combination tooling being the weakest link in the tool. Could you elaborate a little bit on that point?
Yeah, definitely. Uh, the tool geometry is all going to wear at different rates. So if we're combining, say, an end mill and a drill and a top chamfer on the one particular tool platform, typically what we see is the end mill portion of that drill is going to wear out more rapidly due just to the way that it's used and the interrupted cutting nature of milling versus drilling. So we'll see that as soon as that end mill portion comes to end of tool life, that combination tool's done for good. It's done at that point, but that drill point on the end of that tool could still have some tool life left in it. It could still be usable. But because one portion of that combined geometry has extinguished itself, the tool as a whole can't be utilized any further.
Great. And we do have another question here. Does trying to combine several operations onto one tool limit you as a tool maker with geometry options?
That's a good question. Not as much as it used to. I will say, having been in this business since the late '80s, it's amazing how far technology has come, not just in our world but in our industries. So we do have the ability to do way more than we ever did. We have the ability to really dissect our grinding programs and really individualize them way better than we ever were able to in the past. However, we do run into situations sometimes where by combining a lot of geometry onto one tool platform, we're not able to get as creative or as extreme on some of our geometries as we may be if we broke each of those geometries out individually. For example, in the tooling industry, a real big buzz, and one of the things that we at SGS are very well known for as the people that brought it to the market is variable geometry end mills. Varying that geometry in order to counteract some of the harmonics that happen in the machining environment. And when you're trying to combine a bunch of geometries, sometimes you have a limit on just how extreme you can go with some of those strategies on the geometries.
Terrific. Well, I don't see any more questions coming in, so I really appreciate everyone's attention. And Jason, thank you for a wonderful presentation today on the
Well,
combination tool.
well, thank you. Thank you for your time, and thank you everybody for taking time to listen to me speak.
Have a great afternoon, everyone.